All right, everyone. Today's lesson's not too bad. It's a bigger topic second semester, but this is a good time to kind of introduce it while we're practicing other things. So this is a topic revolved around something called finding absolute extrema. So absolute extrema. First of all, extrema, what does that word mean? Those are maximums and minimums. So we've already been finding relative maximums and relative minimums. So what is an absolute maximum and an absolute minimum? Well, if I have, that was really bad. Let's try it again. First one was kind of bad. The second one was really bad. If I have a function that looks like this, let's say, and I talk about it on this interval from here to here. If I have an enclosed interval, so in the interval from A to B with brackets, meaning I'm including the endpoints, so from here to here, this graph has a spot where it's at its absolute lowest, or the absolute minimum, and its highest, the absolute maximum. So let's talk about where that is. First of all, the absolute max. If you notice right here, we have a relative max of this function. But if you notice here at this endpoint, that's the actual absolute max. It's the highest point. It reaches the highest point. So in this case, the absolute max occurred at an endpoint. There is a point that is the highest point in an interval, and that's called the absolute max. How about the absolute min? Well, we have this endpoint and this endpoint, and we have this down here, which is the relative min. And it also turns out that that's the lowest point of the entire interval too. So we call that the absolute min. So the absolute min in this case occurred at the relative min. And the theorem that says there's always going to be an absolute max and an absolute min, we talked about it a while back. It's called the extreme value theorem. The extreme value theorem says these two things have to exist in an interval as long as the function is continuous. It doesn't even have to be differentiable. It just has to be continuous. If the function is continuous, there has to be a lowest point, there has to be a highest point. It has to. And these occur at either endpoints or critical points. So how is this helpful? If I give you a function, like the one I'm about to give you, 2x minus 3 squared times x minus 5. And I give you the interval. And let's say my interval is from 0 to 6. I may ask you to do something like find the absolute extrema. Okay, so how do we do that? Well, we need the derivative because we need to find the critical points. So the derivative is, and we've done a lot of these now, so hopefully this is okay. Derivative of the first, 2 times 2x minus 3 times the second. And then times another 2 because it's a chain rule, right? I missed a 2 there. So it's 2 times this to the first times the derivative of the inside plus derivative of the second, which is just 1, times the original first. And I've done enough of these to know that I can factor out 2x minus 3. And I'm left with a 4 times x minus 5 plus another 2x minus 3 that didn't get factored out. And that simplifies to this derivative 4x plus 2x is 6x minus 20 minus 3 is minus 23. So here's my derivative. Set it equal to 0 to find your critical points. So by setting it equal to 0, I get the two critical points of 3/2 and 23 over 6. Okay, so now that I have the critical points, here's how it works. To find the absolute extrema, I know that the absolute max and min have to occur either here, 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 or here. Absolute extrema occur at critical points and endpoints. So I gotta basically figure out of these four which one's the biggest and which one's the smallest. So I'm gonna find all four of these values. I'm gonna find f of 0. I'm gonna find f of 6. I'm gonna find f of 3/2. I'm gonna find f of 23 over 6. Find all four of these values. The highest one is going to be your absolute max, and the lowest is going to be your absolute min. So I'm going to cheat now because I don't want to do this by hand and use the graphing calculator just to plug in these values. So remember, you just took a quiz where some of you guys were trying to find these by hand. If I'm allowing you to use Desmos, watch. You just create the function 2x minus 3 squared times x minus 5. And then you can ask it to find the values. We can ask it to find f of 0, f of 6, f of 3/2, and f of 23 over 6. So when I look at this guy, where does the minimum occur? It looks like it occurs at this endpoint, or this endpoint f of 0. So the minimum occurs at f of 0 because we have a value of negative 45. Let me write all these down first, and then we'll talk about how I want the answers, like the notation of the answers. So f of 0, f of 6 is 81, f of 3/2 is 0, and f of 23 over 6 was negative 25.407. Okay, so where's the absolute max? This is the absolute max, and this is how you write it. You say the absolute max value is 81, and it occurred at x equals 6, or you could just give me the coordinate 6,81. But this notation is going to be very important second semester, where I say the value and I say where it occurred. And then the minimum is right here. This is the absolute minimum in this interval. The absolute minimum value is negative 45, and it occurred at x equals 0 at the endpoints. So this one was kind of a not fun example. It was just basically the endpoints were our extremes, our absolute extremes, and the relative max and mins weren't as high or low. And then looking at the graph, there was the 3/2, 1.5. It was a relative max, but it was not the absolute max. And then here was 3.833, 23 over 6. It was a relative min, but it was not the absolute min. That's basically all we're doing. Now, one more thing, and we'll do a lot more this second semester. When I did this part right here, and I identified all of the critical points and endpoints, I call these the candidates. They are the places where the max, absolute max, and absolute min can occur. So second semester, I'll really go into this idea of candidates. It basically means where they can occur. So you're going to start by listing the candidates and then finding each of those values. All right, so let's do one more example of this. Same setup. Here's your function. F of x equals x ln x plus x. And the interval is going to be a little bit weird, 0.1 to 2. The reason I chose 0.1 and not 0 is because you can't plug 0 into this. I need to have solid endpoints. So 0 would give me undefined because natural log of 0 is undefined. So this is the interval, and let's say find the absolute max, absolute min of this function. Okay, obviously we can graph it and look. The point is to be able to do this without a graph, especially because second semester it's not going to be this simple. Okay, you'll see why later on. So first thing we got to do is find the derivative. Another product rule: derivative of the first times the second plus derivative of the second times the first plus the derivative of x. Derivative of x is just 1. So looks like my derivative is, this all just becomes 1. So natural log x plus 1 plus 1, so plus 2. There's my derivative. Set it equal to 0. Natural log x plus 2 equals 0. So natural log x equals -2. And then how do I get x by itself? You e both sides. So x equals e to the -2, which is the same as 1 over e squared. It's a super tiny number. So that's your critical point. So this is typically how I do it. I say my candidates are x equals 0.1. So I'm going to need to find f of 0.1. F of 2. So I'm going to find f of 2. And I'm going to need to find f of e to the -2. And we get these by plugging back into the original function. We're trying to figure out these values in the original function. So we'll bring it back. We have x ln x plus x. 0 is undefined, like I said, but we didn't do that. We did 0.1. F of 2. F of e to the -2. So check it out. 0.1, we have -0. And I just lost it. 0.13002. F of 2, we have the value of 3.386. F of e to the -2, we have -0.1353. So, who wins? Well, if you notice, this is the lowest value. That's your absolute min. So again, you could say it occurred at this value. It occurred here at this x coordinate, and this was the value, -0.1353. And the absolute max occurred at the endpoint. So this was the absolute max. That's the idea. We do a lot more of this stuff second semester. Because second semester we don't start with the original function, we start with the derivative, and we have to find all this. So that's a whole thing. We're not going to learn that right now. In motion, rather than say absolute max or absolute min, they'll ask you the same exact problem, but when is the particle farthest left or farthest right? And that's the same thing, because if you think about back to the position graph, you're moving left, 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 and then you move right, right, right. I could ask you when is the particle farthest left or farthest right, and that would be the same process. But again, we'll do more of that second semester, so you don't need to worry about that as much right now. In terms of motion, we apply it. We kind of combine this with motion second semester. But that's the idea. Absolute extrema means find the highest point and lowest point in the original function. And to do that, we find the candidates, which are your endpoints and your critical points, and then you just find those values. And when you find those values, you plug back into the original. Okay. So hopefully you're keeping all this stuff straight in terms of critical points or where the function levels out. But at the end of the day, I'm using the original function to find the value. I want to figure out the actual value of these points in the original. Alright, and I think that's it. Goodbye.